All right, so let's talk about heat capacity here. So specific heat capacity has to do with changing the temperature of a substance. Okay? Do all substances heat up at the same rate? No, they don't. Okay? I mean, you probably notice typically that metals heat up kind of fast. Okay? Non-metals heat up kind of slow. Okay? In general, that's a pattern. Okay? Everything has what we call a different specific heat capacity, and that is how much does its temperature change per joule of energy that I put into it. Okay, everyone follow me there? All right, so it's a physical property, just like density is a physical property, okay, or solubility is a physical property. Specific heat capacity is also a physical property. Okay, if we're dealing with just a particular substance, then we deal with that substance's specific heat capacity because it's specific to it. If we're dealing with an object that's a mixture of many substances, then we have to deal with that object's heat capacity or average heat capacity. Most of the time we're going to be dealing with specific heat capacity. All right, so that's the difference here in these two definitions. Okay, heat capacity is the amount of heat required to raise the temperature of an object, okay, by 1 degree Celsius. That object then is obviously a mixture of many materials, okay, and its heat capacity is kind of an average of all of them. Okay, so that definition applies only to objects, okay, that are made of a mixture of several substances. Okay, pure substances deal with this. Okay, so specific heat capacity, which is the one we're going to deal with more often, is the amount of heat required to raise the temperature of 1 gram of a material by 1 degree Celsius. 1 gram by 1 degree Celsius. Okay. All right. The formula we use for that is E equals mc delta T. What does delta stand for again? Change. What's capital T stand for? Temperature. Okay, so really this is saying mass times specific heat capacity times final temperature minus initial temperature. Okay, but we usually just say delta T because we do that in our head. Okay, or it just says it changes temperature by 50 degrees. Okay, something like that. So it's not usually an operation you have to do. Okay, just looks easier that way. Now, manipulating this formula, pretty easy. Everything's multiplied together here, right? So if I want to solve for anything on this side, what do I do with the other two things? Divide them over. All right, so if I want to solve for delta T, I divide by mc. If I want to solve for m, I divide by c times delta T. If I want to solve for c, I divide by m delta T. Okay, I just bring the other two parts over. So it's really, really easy to manipulate. Okay, so what everything stands for, E is the energy in joules. Okay, the units for energy are joules. Mass, okay, M is the mass, and that is always going to be in grams. Okay, this is a chemistry thing. All right, chemistry deals with small stuff, so it's always in grams. Physics, we go big. Okay, physics is kilograms. All right, and then delta T is the change in temperature of the substance, and usually that's going to be in degrees Celsius, but it could also be in Kelvin, but it's usually in degrees Celsius. Okay. All right. Questions on how that works? Okay. So with our specific heat capacities, okay, what's something that typically takes a lot of energy to heat up? Think of anything? What's that? Well, actually, metal heats up really fast. So if it heats up really fast, it actually doesn't take very much energy in order to heat it up. As an example, okay, specific heat capacity of gold. I think I have them all here, don't I? No, I don't. Okay, specific heat capacity of silver is 0.230 joules per gram degree Celsius. Okay, that means it takes less than 1/4 of a joule to change the temperature of a gram of silver by 1 degree Celsius. Is a joule very much energy? No. Okay, so 1/4 of a joule is really a small amount. Okay, something like water. It's 4.2 joules per gram degree Celsius. It takes a lot of energy to heat water up. I mean, if you ever have to boil like a kettle of water, I mean, A watched pot never boils. Don't stand there and watch it. That's just an expression. It does boil, actually. It just takes a long time. Okay, it does. It takes a long time because water has a very high heat capacity. 4.2 joules for every gram of the water by 1 degree Celsius. Okay, so if we're talking about, taking water from room temperature and heating it to boiling, okay, we're talking about a fairly large amount of energy. Can we calculate how much? Okay. Let's say it's a liter of water. What's the mass of a liter of water? Oh, tricky question. 1 gram of water is 1 milliliter of water. How many milliliters in a liter? 1,000. So, what's the mass of 1,000 milliliters of water? 1,000 grams. Okay, so let's see if we can figure that one out. Okay, so we got 1,000 grams of water. Okay, and we're trying to figure out how much energy it will take to heat it from 20 degrees Celsius to 100 degrees Celsius. All right, so I'm going to go E equals M times C times delta T. Okay, the C for water I just gave you, it's 4.2 joules per gram degree Celsius. And I'm multiplying that by the change in temperature. And I'm going from 20 to 100, so that's how much? 8. Okay, so we punch that in. Okay, so 1,000 grams times 4.2 times 80. 336,000 joules. Is that a lot? That is a lot. Okay. If I wanted to do the same thing with silver, it would take considerably less. If I had a kilogram of silver, though, I'd run away. A kilogram of silver would be worth a lot of money. Okay. Okay, times 0.230. Okay, times 336,000. Oh, sorry, by 80, not 33,000. That would really screw up my point. Doesn't take very much energy to heat up a piece of silver, okay, by that much. All right? I mean, think about it, guys. If you put your hands in cold water, your hands get cold pretty quickly, right? But if you put on, let's say, like a ring that's made out of silver or gold, it feels cold for about a second, and then it's pretty much the same temperature as your body because they heat up quickly. They have a low specific heat capacity, so they don't take much energy before their temperature is changed. Okay, whereas water is quite a bit different. Okay, and again, this goes back to that whole climate thing that we were talking about. Water has a really high heat capacity. So if you live near the ocean, can it hold a lot of energy? Yeah. So if the air temperature around the ocean drops, the ocean has a lot of energy that it can give to the air, and the ocean's not going to change temperature very much because it can lose a lot of energy without changing temperature. It kind of goes both ways. Okay? Yes, it takes a lot of energy to heat up the ocean, but when the ocean starts to cool, it can give off a lot of energy without changing its temperature very much. Okay? So that's the reasoning behind being close to an ocean, being able to regulate your climate. Okay? I know I'm always tying it back in, but that's kind of the most important part of this whole unit. Okay? All right. Now, I am going to give you guys a handout that's got the specific heat capacities of some common substances on it. Okay? But what I want to do first is go through a couple of examples here. Anytime we get a new formula, Coder goes through all the manipulations of that formula. Okay? So that's what we're going to do here. So I'll have you write this one down, okay, and I will send that sheet to the photocopier. Pretty straightforward here. Okay? Write down our givens. We're looking for how much energy. Okay? We are told the mass, okay, 150 grams. We're told the specific heat capacity, 4.2 joules per gram degree Celsius. And we're trying to change the temperature from 5 degrees Celsius to 85 degrees Celsius, which is, again, an 80 degrees Celsius temperature change. All right? Again, I always just do that part in my head. It's not usually a difficult mathematical operation. I'd prefer to have a number here than to have two numbers in brackets that I'm subtracting later. It's just easier to use. Okay, so E equals M times C times delta T. So we have our 150 grams times the specific heat, 4.2, okay, times our 80 degrees Celsius. Right, so 150 times 4.2 times 80 degrees. Okay, is 50,400 joules. All right, pretty straightforward. Okay. Write that one down and give it a try. Okay, so for this one, we have the mass. It's 100 grams. Okay, we're told that we have 4,200 joules worth of energy, and that we're changing the temperature from 12 to 62 degrees Celsius. Okay, so we're just going to go 62 minus 12, and we're going to get that the temperature change is 50 degrees C. All right, E equals mc delta T, and we're trying to solve for what the material is, so the specific heat capacity. So we'll divide both sides by m delta T. Okay, and we'll plug in 4,200, okay, divided by our mass, which was 100 grams, times 50. And this part, obviously, you have to do in brackets. Okay, it needs to be done before. If you just type 4,200 divided by 100 times 50 without the brackets in your calculator, you don't get the same answer. Okay, so 4,200, okay, divided by, and then we got in brackets 100 times 50. All right, and we get 0.84, which is the specific heat capacity for glass. Okay, and when sorry, I did this. What did I not do here that I should have done? This answer doesn't have any units. Okay, that would be a bad thing to do. Joules per gram degree Celsius. Okay, if you forget that that's what the units for specific heat capacity are, just look at what you did here. This was in joules, this was in grams, and this was in degrees Celsius. Joules divided by grams times degrees Celsius gives you the proper units. Okay, so if you're ever in doubt, that's where those units come from. Okay, all right, and like we said, that was glass. All right, I'm just going to go through these two just so we get them done before class ends. Okay, what's the final temperature of a 0.85 gram, 185 gram block of iron initially at 7 degrees Celsius if it's heated to 200? So they're giving me one of the temperatures and asking me to find the other. So what part of mc delta T do I need to find? If it has to do with temperature, I should find T. I'll find the change in temperature using E equals mc delta T, and then I'll be able to use that and the initial to figure out what the final is, right? If I know where I started and I know how much I change it by, I can figure out what my last temperature would be. Agreed? All right, so our energy here is 200. Okay, and our initial temperature is 7 degrees Celsius, and our mass is 185 grams. And we know it's iron. Sorry, iron is what, 0.18 something? No, 0.43 something. 46? All right, 0.460 joules per gram degree Celsius. Okay, so I'm going to solve for delta T here. Delta T is going to be E divided by M times C. So 200 divided by 185 times 0.46. Whoops, 200, not 185. Come on already. Always when you're in a hurry, right? Okay, 200 divided by 185 times 0.46. All right, so my temperature change is 2.3 degrees Celsius. So I add that to 7. My final temperature is 9.35 degrees Celsius. All right, we'll see you guys tomorrow. Oh, no quiz tomorrow, but there will be one Tuesday.